Hello, welcome. Today we will begin the section on t-tests. Specifically, we'll be learning about what is called a one-sample t-test. First, we will start with a quick review of the z-test. We've gone over this test many times, but I think it is helpful to take another quick look at it because you'll soon see how the one-sample t-test is very similar to the z-test. You might remember that we use a z-test when we want to compare a sample mean to a population mean, and when we know the population standard deviation. To perform a z-test, we're going to first calculate a z-obtained value. To do this, we will take our sample mean, denoted here as a capital M, and subtract our population mean. We will then divide this value by the population standard deviation, which is divided by the square root of n, which, if you will remember, is the number of participants in our sample. You may recall that this denominator value has a special name. It is called standard error, which is the standard deviation of the sampling population. So let's do an example of a z-test. Let's say we have a sample of 25 students and their mean IQ score is a 108. We know that the population mean IQ is 100 with a standard deviation of 15. Now, remember that the null hypothesis says that the sample mean is really no different from the population mean. The null hypothesis assumes that any difference between these two means was due to chance. So let's see if we can reject the null hypothesis. We can start by plugging in our values and start reducing. You'll see that we are left with the z obtained of 2.67. Next, we need to determine our z critical value. For a one-tailed test, the z critical value will always be positive 1.64 or negative 1.64 when we have an alpha of 0.05. Remember that alpha represents the maximum amount of risk we are willing to take in making a type 1 error, which is when we reject the null hypothesis when it is actually true. For a two-tailed test, we look at both sides of the normal distribution. So our z critical values are going to be positive 1.96 and negative 1.96 when we keep our alpha at 0.05. Once we have our critical values, we can compare them to our obtained value, which you'll remember is 2.67. And we know that our obtained value of 2.67 is greater than the critical value of 1.96, but sometimes it's useful to visualize what is going on by plotting our obtained z-score on the normal distribution. When we do this, we can see that our obtained value of 2.67 clearly falls in the critical region, which is also known as the rejection area. So, can we reject the null hypothesis, which states that the difference between our sample mean IQ score and the population mean IQ was due to chance factors? Well, yes, we can reject the null hypothesis because our z obtained value is greater than our z critical value. So what is our p-value? And that's the chance of making a type 1 error if we reject the null hypothesis. Well, only 2.5% of scores exists in the critical regions for this two-tailed test. So the likelihood that we would get a z obtained value greater than positive 1.96 or negative 1.96 is less than 5% in total. So the chance of making a type 1 error by rejecting the null hypothesis when we should have retained it is less than 5%. Thus, the p-value is less than 5%. Now, what if we wanted to compare a sample mean to a population mean but we don't know the population standard deviation. Well, we can't use the z-test because that requires the population standard deviation. Instead, we will use a one-sample t-test. And you can see that the formula for a t-obtained score looks very similar to the formula for a z-obtained score. The only difference is that instead of using the population standard deviation in the denominator, we're going to use the sample standard deviation. Again, this denominator value is known as a standard error. So let's do an example. In this case, our sample mean is 28. The population mean is 24. Our sample standard deviation is 5.5, and we have a sample size of 20. We want to know if our sample mean is significantly different than the population mean. The null hypothesis states that any differences between these means was due to chance, that there's no real difference between our sample and the population. So let's see if we can reject this null hypothesis. We can plug in our values and start reducing. You'll see that we are left with a t obtained of 3.25. Next, we will need to determine the t critical value. Unlike the z-test, the t critical value is going to change as a function of our degrees of freedom and our alpha level. We always use an alpha of 0.05. However, if we are running a two-tailed test, we have to split that 0.05 in half so we can have 0.025 in each tail. That is what we will do here. Our degrees of freedom is 20 minus 1, so we will go down to 19 in the first column of our of our critical t score table. For this example, we're going to use a two-tailed test, so we'll go over to the 0.025 column. Then we will make our way down to the degrees of freedom of 19, and we will find that our t critical value equal positive 2.09 and negative 2.09. Okay. Now we can plot our t critical values to find the beginning of our critical areas or rejection zones. We then plot our t obtained value of 3.25, and we see that we are clearly greater than the t critical value, and we are in the rejection zone. So can we reject the null hypothesis that says there is no real difference between our sample mean of 28 and the population mean of 24? Yes, we can reject the null hypothesis. Our sample mean is significantly higher than the population mean. What is the chance of us making a type 1 error in that we are claiming these means are different when they really aren't? Well, less than 0.05. So hopefully this helps you understand how a one-sample t-test is quite similar to a z-test. Next time, we will take a look at independent samples t-tests, pair samples t-tests, and effect sizes, particularly Cohen's d, which is often used with t-tests.